So yeah, so we're back, and let us reconsider this problem of how information is propagated, sound related information, I must say. We saw this curious situation for supersonic flow. You remember this cartoon where we found that sonic information, in the case where the speed of propagation is larger than the speed of sound, propagates in a rather peculiar way. It's only observers within this thing called a Mach cone, the width of which is roughly the half width of the cone is something like CS over V. Okay, so it's only observers within this Mach cone who receive sonic information, and observers outside this Mach cone do not receive this information. So let's consider this a little more formally now. Let's consider again the linearized mass and momentum continuity equation. If you remember, linearization essentially means considering only the disturbances, only the U1s and the P1s and the rho 1s, and not the U naught if it exists, or the rho naught or the P naught, number one. Number two, linearization essentially means that products of small quantities, products of anything with subscript 1, suppose you have a U1 times grad U1, you neglect that. Anytime you see the subscript 1 being repeated more than once, you neglect that term, because the products of small quantities results in a quantity that's even smaller. So that's what linearization means. And the linearized mass and momentum continuity equation are repeated here. This is the linearized mass continuity equation, and this is the linearized momentum continuity equation, and the dp d rho is of course c sub s squared. So this is what we've already seen, and now we specialize to one dimension for simplicity. So in one dimension, you know, these nablas are essentially d over dx, strictly speaking. Okay, there is no dy and there is no dz. We are only considering one dimension. So anytime you see a nabla, you just say, so for instance, this nabla rho 1 would simply be d rho 1 dx. That is it. Okay, so these two equations start looking like this. In other words, this is this, and this is this. That's all, right? So this is c sub s squared, and we said that nabla rho 1 is simply d rho 1 dx, and that's it, right? So this is the linearized mass continuity equation, and this is the linearized momentum continuity equation in 1D. Mind you, these are valid only for small perturbations, very important. Because, in other words, if there are waves, and there are, and then these waves propagate at c sub s, at a velocity c sub s, these waves are weak, right? Weak in the sense that rho 1 over rho naught and P1 over P naught are much less than 1. This is what we mean by weak waves. Okay, right. So we say this because we will, after we're done discussing this, we will have an opportunity to relax this weak assumption and do something that's very analogous to this. Okay, so but for the time being, we're considering only weak waves, right? So we combine these two equations to write this. This is the addition of both those equations. You see, there's a u over cs, and so I encourage you to see how adding these two equations gives you this, and subtracting those two equations gives you this. Okay, in other words, I urge you to show this. Okay, it's not very hard. It's a simple matter, and so right, I urge you to show this. Now, what you can see from this is that this quantity and this quantity are the same for this equation. Similarly, this quantity and this quantity are the same for this equation. So, the quantity u1 over Cs plus rho 1 over rho naught, which is the same here and here, is constant along the line x minus c sub st equals constant. This is an advection equation. Both of these are advection equations. The top equation represents a situation where this quantity u1 over Cs plus rho over rho naught is advected, is carried along unchanged. That's what advection means. Some quantity is simply advected along. It's carried along unchanged along the characteristic x minus c sub st equals constant. In other words, as long as I ensure that x minus c sub st equals constant, or as long as I am moving in the xt diagram, as long as I am moving along a straight line with speed c sub s in the forward direction, this will always be constant. That's what this equation is telling you. Okay. Vice versa, for this equation, this quantity is advected or is constant along this characteristic x plus c sub st equals constant. This would represent propagation in the forward direction. This would represent propagation in the backward direction. In other words, the quantity j, and now we are simply naming this. Okay, this quantity, okay, rho over rho naught, we simply replace by p over p naught and divide by replace by p over p naught, and that leads to the appearance of this gamma, where we have assumed that p is proportional to rho raised to gamma, like that. Okay, so this quantity propagates unchanged in the forward direction with a speed c sub s, and this quantity propagates unchanged in the backward direction with a speed c sub s. And note, we have dropped the subscripts. There used to be a p1 here, or rho 1, there used to be u1 here. We've simply dropped that, okay, just for simplicity. But you should keep in mind that these are perturbations. Okay, these are not background. Okay, the backgrounds still have the subscripts 0. Okay, right. So these are conserved quantities, quantities that are this quantity is conserved in the forward direction. Okay, along the forward characteristics, this quantity is conserved along the characteristic x minus, and this quantity is conserved along the characteristic okay, right. So now, okay, how do we apply this? So let us consider something called the shock tube problem. If you for the time being, we're not really discussing shocks, not yet. We will come to shocks, but we're not yet discussing shocks. But this is a classical setup for a shock, for studying shocks, both from a analytical theoretical point of view as well as in the lab. And this setup comprises a tube with an airtight piston. Rather, this would be a piston normally, and you shove the piston forward, and you'll find that when the speed of the piston exceeds the local speed of sound, there will be a shock formed in front of the piston, so on and so forth. That's why it's called a shock tube. Just Google a shock tube and you'll find lots of sources. For the time being, we are not considering shock formation. We are, and we are not considering a piston either. We are considering a much simpler situation where you have infinitely long tube like so, and you simply have a diaphragm, an airtight diaphragm with two pressures on two sides of the diaphragm. Okay, you have P1 on one side of the diaphragm, the pressure is P1 on one side of the diaphragm, and the pressure is P0 on the other side of the diaphragm. Okay, yeah, so don't confuse this with perturbations and background. In this case, these are simply background. Both of these are background pressures. P1 and P0 are both background pressures. The difference simply is that there is one background pressure on the left of the diaphragm and there is another background pressure on the right of the diaphragm. Okay, and gas on both sides is initially at rest with P1 greater than P0. Okay, the pressure on the left is larger than the pressure on the right. So this is our setup. Okay, now what do? We rupture the diaphragm. We create a little hole here, right? At t equals 0, time t equals 0, and we see, and what will happen, we know, our intuition tells us that there will be mixing, right? The gas will flow from the left side to the right side because the pressure on the left is larger than the pressure on the right, right? So gas will flow from the left to the right, and let's see what happens, right? So, and we will find that this concept of these conserved quantities is a very useful one in trying to figure out exactly what happens when the diaphragm is ruptured as time progresses, how exactly the gas mixes. So this is very useful. So what is the distribution of pressure and velocity everywhere in the tube? This is the question we want to ask. So you see, information propagates at the sound speed, right? And there is no restriction on which direction the information propagates in. It can propagate to the right and also to the left. In other words, there is a forward wave as well as a reverse wave, right? So the thing is, ahead of the forward wave, the information that the diaphragm is ruptured has not yet reached. Okay, so the gas was initially at rest and it will remain at rest because the information is not yet reached. The gas does not know that the diaphragm has been ruptured. So the background velocity is still equal to 0. And the pressure is still equal to the background pressure, whatever it was. And the same is true behind the reverse wave. There's a wave propagating to the left, which is the reverse wave, and behind the reverse wave, in other words, for the points to the left where sonic information has not yet reached, is the same thing. The gas was initially at rest, the undisturbed gas was at rest, and it remains at rest. The undisturbed gas was at a pressure P equals P1, and it remains like that. So that's fine. So ahead of the forward wave and behind the reverse wave, the conditions are undisturbed, whatever it was prior to the rupturing of the diaphragm. What's interesting is in between. How does the gas mix? So this would represent the reverse wave in the xt. You see, this is x and this is t. So this would represent the reverse wave because x plus ct is equal to 0, and this would represent the forward wave. So and this would represent the reverse wave. Okay, so ahead of the forward wave and behind the reverse wave, so in other words, in this region or in this region, the conditions are undisturbed. Ahead of the forward wave, the conditions are this, and behind the reverse wave, the conditions are this. The question is, what's in between, in here, for any arbitrary point P, say. Okay, for any arbitrary point P, what are the conditions? The thing to remember now is what you do is you link this point P with a line with a forward characteristic that's parallel to this. This is parallel to this, and this is parallel to this. Okay, and the intersection of these two lines will give you the physical conditions at any arbitrary point P here, 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 any arbitrary point P that is within this V-shaped thing here. And let's see how that's done, right? Using conservation of J plus and J minus, what we do, consider a point P that's in between the forward and reverse waves, like we said, this point P. It is connected to the conditions at t equals 0, which we know about by forward and reverse waves. In other words, what's the use of this dotted line and this dotted line? The point is, you see, on this axis t is increasing. So right here t is equal to 0, right? So this connects, this dotted line connects the conditions here to the forward wave, the propagation of the forward wave at t, and this is t equals 0 here as well as here. And we know what the conditions were at t equals 0. Before the rupturing of the diaphragm, we know what the conditions were. We know that u is equal to 0 on the left, on the right, and the pressure is equal to P1 on the left and pressure is equal to P0 on the right. We know this, right? So point P is connected to the conditions at t equals 0 by forward and reverse waves as shown. And since J plus is conserved, which means it means that J plus at x equals xp is equal to J plus at t equals t0. Okay, and J plus is equal to 1 over gamma P1 over P0. This is J plus. Why? You go back to the definition of J plus, you see, J plus and u is equal to 0, therefore all that remains is this, 1 over gamma P over P0. That is why J plus at t equals 0, u was equal to 0, that's why, and that is equal, therefore all that remains is 1 over gamma P1 over P0. Okay, there's a little bit of a confusion in signs. I said that I was dropping the subscripts 1, but here I have retained the subscripts 1. But what that means, this P1, it's really not P sub 1. This is really P1, not P sub 1. Okay, this one. This really should be P1. P, yeah. So, and the gas is at rest there, as we said. By the same logic, J minus at x equals xp at the point P is equal to J minus at t equals 0, and J minus at t equals 0 is simply equal to minus 1 over gamma. Why is that? You see here. J minus is equal to, this is obviously 0 because u is equal to 0, and so it's whatever condition, whatever pressure there is divided by P0, but you see P is simply equal to P0 along J minus. You see out here, when you go along this characteristic, we know that on the right is simply equal to P0. So P0 over P0 is simply 1. That's why we get J minus is simply equal to minus 1 over gamma. That's why we say J minus at t equals 0 is simply equal to 1 over gamma. Okay, right. So what's the objective of this entire exercise? We want the speed and the pressure, and therefore once we know the pressure via the sound speed, we can relate it to the density also, right? So we want the speed and the pressure at point P, at the point x sub P, right? So therefore J plus is equal to 1 over gamma P1 over P0, and again I apologize for this, this is really P1, not P sub 1, okay, sorry. And J minus is this is 0, and P over P0 is just, it's essentially P0 over P0, so it's simply minus 1 over gamma, right? So there are two linear equations. So I want P, right? So at x equals P, I don't know U, I don't know P. I don't know U, I don't know P. So there are two unknowns. There's a U and the P, and I have two equations, right? So there are two unknowns U and P, and there are two equations. So, and I just solve them. So this enables us to solve for the conditions in between the forward and reverse waves. At any given point, which is characterized by a velocity U and a pressure P, I can figure out what U is and what the velocity is and what the pressure is by solving these two linear equations. The right hand sides are completely known. P1 is given to us, P0 is given to us, gamma is assumed to be say 5/3 for a monoatomic gas, right? So essentially what this is saying is that the conservation of J plus and J minus enables us to solve for the conditions in between the forward and reverse waves. In other words, anywhere here, anywhere in this V. So that's what this enables us to do. Okay. Now, a variant of this problem is one where the pressure imbalance is created by a piston. So instead of a diaphragm, what you have is a piston, and the piston is moving inside the tube at a fixed speed u. Okay. So what you have is a piston. So you have the same shock tube. Right, and as before, you have P1 and P0. The only difference being the piston is moving at a velocity u. This piston is moving at a velocity u. And what happens? Same question we are asking, right? The observation point, so again you have forward and reverse waves. So the observation point P also connects to the piston with a forward wave. The piston can only, since it's moving forward, it can connect to any observation point here only via a forward wave. But we know the velocity of the piston. So the velocity of the piston is known, but not the pressure. The velocity of the gas right at the piston is known to be u, simply because the gas is sticking to the piston, isn't it? So the gas is sticking to the piston, so the velocity of the gas at the piston is known, but the pressure is not known. Okay, so that is one thing. So as we said, the gas is being pushed by the piston, right? So right at the surface of the piston, since I know that the piston is moving at a velocity, u, the velocity of the gas is also u, right, at the piston. But I do not know the pressure of the gas at the piston. This I don't know, right? So I don't know the pressure at the piston. I know the velocity, and the velocity of the piston is given by u, but the pressure is not known. That's okay. But the piston is connected to the x-axis by a reverse wave. Okay, the observation point is connected to the piston by a forward wave, but the piston is connected to the x-axis by a reverse wave. So what happens is you have a given observation point like so, and the observation point is connected to the piston via a right, and the piston is connected to the x-axis via a reverse wave, and the point P, of course, as before, the point P is also connected to the x-axis via a reverse wave, right? So P is connected to the x-axis by a reverse wave. To the piston, P is connected to the x-axis by a reverse wave, to the piston via a forward wave, and the piston itself is connected to the x-axis via a reverse wave, right? So what gives now? The thing is, additional unknown, if you see in comparison to the previous problem, is that we do not know the pressure right at the piston. We know the velocity, but we do not know the pressure right at the piston. So we have one additional unknown, but we have one additional, so we have three equations, 1, 2 and 3. So we have one additional unknown in comparison to the previous problem, but we have one additional equation. So no problem. So it can be solved just like the previous problem. And I encourage you to go ahead and solve. This problem too. Right. So this illustrates the utility of considering characteristics. Okay. The important difference being that we have in this treatment we have restricted ourselves to smart perturbations, and therefore weak waves. In what we will treat going ahead, we will relax this assumption, but before that, and when we relax this assumption, the perturbations will be large, and so that's the essential difference, and even there we will find invariants. Okay, but let us see what happens qualitatively. Let us first try to understand what happens when the disturbances are not small. In other words, what happens when the waves are not weak. Okay, we will encounter this phenomenon called steepening. Okay, and let us try to understand this qualitatively first. So let us say that this represents the profile of a pressure pulse. Okay, so this entire thing represents a pressure pulse, right? So the pressure is large here and it's small here. Yeah, so this is a pressure pulse that's propagating in space. So this is essentially x-axis, and the y-axis is just P, pressure. Okay, so the pressure is larger here as compared to here. That's the main point. And so because the pressure is larger here as compared to here, the speed of sound, say c sub s, let's call this c sub s2, and let us call the speed of sound here as c sub s1. Clearly, because if we consider that the density at both these points is the same, clearly c sub s2 is greater than c sub s1. The speed of sound here is larger than speed of sound here. That's obvious, no problem there. In other words, the top of the pulse is moving faster than the bottom of the pulse. And if it's c sub s1 here, it's something like that here too. A symmetric point, so I should also draw here. Okay, so the sound speed at the top of the pulse is larger than the sound speed at the trailing edge of the pulse as well as the leading edge of the pulse. Okay, in other words, one can envisage a situation where the top of the pulse, the sonic information from the top of the pulse can overtake that from the leading edge of the pulse. You see, so the top of the pulse kind of tries to overtake the top of the pulse, which is trailing this edge, one can envisage a situation where it overtakes the leading edge and the pressure pulse starts looking like this. Okay, now this is a problem. Why? If you draw a dotted line like so, you see, it intersects the pressure pulse at 2 points. 1 and 2, and in fact 3. Okay, now this is not allowed. What is the pressure here? Is it this or this or that? You have to give me a definite answer. You cannot say maybe this, maybe that, maybe no, you cannot say that. It has to be one answer. In other words, yeah. So eventually what happens is this kind of a situation is not allowed, okay. And eventually what happens is this kind of a situation leads to a steepening, okay. And this marks a pressure discontinuity. That's what happens. These kinds of things are not allowed, okay. And instead what happens is this steepens and forms a discontinuity like so. And this is what a shock is essentially. It represents a discontinuity in physical quantities such as pressure, density, for that matter velocity also. And this can only happen when the amplitude of the pressure pulse is so large that the sound speed is appreciably larger at the top of the pulse as compared to the leading edge of the pulse, or for that matter the trailing edge of the pulse. If the pressure pulse was small, the difference between CS2 and CS1 would not be that much. These kinds of effects start becoming noticeable only when the pressure pulse is so large that CS2 is appreciably larger than CS1. Okay, and when that is the case, the waves are no longer weak, and we start seeing these kinds of phenomena, which lead to discontinuities. It's essentially a mathematical problem. Okay, and it's not simple. Point is, we would not be talking about this if it was simply mathematics. The point is, pressure waves, shock waves are indeed observed in everyday life, both in the lab and you guessed it, they're very, very important in astrophysics, which is why we're starting to talk about shock waves at all. And this happens when we will see that it happens A, and when the speed of an object exceeds the speed of sound, B, when the pressure disturbances, when the disturbances of pressure or density or whatever are so large that the linearization assumption that we made all along is no longer valid. So we will stop here and we will take up a detailed study of shock waves when we meet next. Thank you.